Hi guys. Well, what do you think about all these things here? I think we're stuck in a loop. And the loop is called teardown loop. Because why? It's a teardown again. I didn't plant it, but it happened. So what is all this stuff here? Why do I am showing you that, all these things here? Look, this one, this makes blink blink, etc. Many of those things you have already seen. For example, this one is an USB and serial RS-232 GPS GNSS receiver. This is my NTP server, GPS discipline NTP server that I already made 2 videos that I will link in the description. From that, of course, I will have links in the description too. And as a last thing, this thing, the bigger one, that is my let's say so DIY GPSDO, where I got GPS discipline oscillator from an old analog television transmitter from PLISCH, and I converted it to a desktop appliance. I've made a video of that too. Wasn't very interesting because I didn't got many views, but perhaps the video that I did was not good at all here. Anyway, if somebody is interested on this design, because it's quite a lot of electronics I added inside, let me know. I will make another video. The electronics are on the back side of the front plate and on a second PCBs, that is for the power supply and the fan control. Anyway, why I'm showing you all these things? Because all these things have one thing in common: GPS reception. And I need GPS reception to synchronize this thing here. To synchronize, to stabilize the oscillator or the OCXO inside. I need it for that, for the precise time, for the NTP server, and for the receiver for whatever I use it. But my problem at the moment is that in the room where I am, it's my living room, and I have absolute no reception. No GPS reception, nothing, nada. This is why this long RG174 is connected all the way through the room out to the balcony where the external antenna is. This is a pain. This is annoying. Not only annoying because I can use it only once, or if I want to use more, I have to make some kind of splitter, adapter, splitter, something. But even if I use a splitter, I have a lot of cables to all these devices, and there are devices that have an embedded GPS antenna, then I cannot use it anymore. And to show you how bad the situation is, look. So, this is how it looks when I have connected directly the external antenna on my USB receiver. This thing. You see, it has a 3D fix, it's blinking in the PPS LED is blinking. I see a lot of satellites. I see the GPS satellites, the GLONASS satellites, and the Galileo satellites. These are the 3 constellations I have configured in the U-blox M8N module that I have in the receiver. Perfect. But only when I have connected the external antenna. So what happens with an internal antenna? So now I connected the internal antenna that is on the table, like you see it here. And what you see? Zero, zip, nothing reception. And this is the reason why now I need a solution. And the solution is called GPS, GNSS Repeater. So the video today will be all about GPS/GNSS repeaters. Everybody knows GPS, it's Global Positioning System. GNSS is a little bit, the wording not very well known. It's called Global Navigation Satellite Systems. And this over term for all the available GPS systems that exist. For the moment, the more important ones, the more used ones are four. It's the GPS, the American system. It's the Galileo, the European system. It is the GLONASS, the Russian system, and it's the Beidou. It is the Chinese system. So there are at least four major systems that provide same functionality, positioning and precise timing. So you can imagine the sky out there is quite crowded. To avoid now to have all the time running a cable through the room or making splitters or I don't know, whatever, I said, okay, I will use a GPS repeater. A repeater is nothing else that will take the signal from outside, from the antenna, and will redistribute it into the room, retransmit it. Here I have, for example, a design I made in my job professionally. It is a very much more complicated design. You have the antenna, physical antenna on the rooftop. You have a converter that is from coaxial to a fiber converter. Here I'm using, everything is the coax is only when it comes from the antenna to the converter and from the converter to the transmitting antenna. Everything else is single mode fiber because of the distances and the immunity to noise. This is a design I made for a special location. Anyway, you have the converter to a fiber optic. You go whenever you go. I have a passive splitter there, 1-to-8, an optical splitter, and I have everywhere then connected again with fiber optic, with a single mode fiber optic to the reconverter, let's say, so that goes from light fiber, single mode fiber to the coax and to the retransmitting antenna. This is how it looks. This is a design that is for a very large location, up to kilometers away, and it uses a technology called RF over fiber. That is nothing else, well, nothing else. It is you modulate the 1.575 something gigahertz you have on a single mode fiber on light, and you demodulate it again back on copper, and you use passive antennas for retransmission. Just for information, this is a small part of my professional daily job. Yeah, this is only one. And this RF over fiber, I know I'm getting away from what the video is at the moment, but I just want to show you what RF over fiber means. It's used for environments that are very noisy or that you do not want at all to have any noise. And another design I made 2013 using RF over fiber is to transmit all the channels of 4 complete satellites over one single mode fiber, so you can provide hundreds and many hundreds of channels over one single mode fiber for all the city. The idea was, the design was called virtual satellite dish. And the idea was to eliminate the many satellite dishes that you have everywhere, because everybody from every ethnicity, from wherever he is, he wants to see his home channels. This one, I took the 4 more important satellites with the most ethnic channels on it that cover 99% at least of the population of the city that was planned to. And they had everything. And the thing is, it is only 4 satellites. I can do 16 satellites if I want. The thing is just multiplexed. It is a little complex here. Sorry guys that I'm speaking so much. I used a DVDM multiplexer. After that it was a switch for a second head end. And then there were special a splitter, and then a special devices called EDFAs, Yttrium Doped Fiber Amplifiers. These are high power laser output devices that could go up to 30 kilometers. So this was planned for a complete city. You see when it was, 2013. Anyway, sorry guys, I just wanted to say what RF over fiber is, but this is not something I will use. I checked the internet, of course eBay, to find something that is suitable for me, and I found this contraption here. Well, I know this thing under so many names. It is used, many vendors sell it. Look, for example, here we have one vendor, we call it RK104. It's a kit that consists of the GPS repeater, GPS GNSS repeater, the external antenna, a lot of cable, like here, for the connection between antenna and GPS repeater, and the power supply. Another vendor calls it RA200. Another German vendor calls it, I think, AS47. It's the same generic thing. That is, let's say so, at the bottom of the professional range. And even that this thing is at the bottom of the professional range, the kit itself with the external antenna, the cable and the power supply costs more than 1,000 euros. Anyway, I bought this for ridiculously 30 euros, yeah. And this is what all the video is about today. The teardown of this one, based on the schematics. I made reverse engineering of the schematics. I will show you how it performs. Spoiler, spoiler, not very well. For example, here the one vendor says up to 10 meters, and the other says, what does he says? 20 to 30 meters. So honestly, they write what they want. It's exactly the same thing from the same Chinese manufacturer, just rebranded with thousands of names. I will show you this one, how it works, how it performs. The schematics, we'll go through the schematics. I will explain a few things. And depends on how this video goes, and how long it will take, will be either a one-part video or a two-part, because I have a second absolutely low-cost GPS repeater, and you will see how it performs. This thing, the second one, consists of two pieces, the external antenna, that again I made a teardown, and the reverse engineering, and the repeater itself that also has been reverse engineered and made a teardown. So okay, but we will start with this one. By the way, guys, if you are interested in my videos, if you like my videos, if you like constructions like this, you will see how it looks inside. It looks interesting. Please remember to subscribe my channel, press the notification button so you get informed when I upload new videos, and press the like button if you like what you see. So let's see what's inside of that. So, and as we wait to get the best performance of the repeater, I want to show you the frequencies that I used for the GNSS systems. We are at the moment at the upper L band. It's 1.500 gigahertz. And the three of the GNSS systems, the Baidu, the Galileo, and the GPS, using a center frequency of the E1L1, the 1 frequency of 1575.42 megahertz. It's quite a high frequency. And the only one that is out of that range of the G1 frequency is GLONASS, that uses 1600.99 is the center frequency. And we will see what that means in a while. Let me show you through my living room. So this is how the thing is connected. It goes from the coax cable, with the coax cable to the external antenna. Yeah, here you see it. 9-volt supply, and it is almost at 2 meters high. And this is where the GPS antenna is. That's a distance of more or less 5 meters. So, and this is how it looks after half an hour of synchronizing. What we see here is that GPS and Galileo, nullo problemo, no problem at all. Because we have here, as you can see, E1, L1 at the same frequency. But what we are missing is GLONASS. And when I showed you before, when I had directly connected the antenna to the receiver, we saw at least 6 GLONASS too. This is because the signal retransmitted from the repeater is not enough. It is too weak to amplify the GLONASS itself, and you will see why. Remember, GLONASS 1600 megahertz. Yeah, it's out of the range of the 1575 central range. Now we will see why this happens based on the schematics. So now we have the first layer opened. I didn't want to bother you watching me unscrewing screws. This is the first layer. And what we will see here, that's the antenna. That's a retransmitting antenna. This thing shows down, and it's called a helical or helix antenna. It has 1, 2, 3, I think it's a trifilar. 1, 2, 3, 4. It's a tetrafilar. It's called a tetrafilar helix antenna. Helix antennas are used mostly in, sorry guys, in the high quality receivers and transmitters. Are much more expensive than patch antennas that you will see in as it looks the next video. because this video is getting already too long and I'm not finished in any means yet. So this video will be just for this repeater. And in the next video, I'll show you the absolute jelly bean, like Dave Jones says, the very cheap one. But this is the semi-professional one. Remember, this kit cost over 1,000 euros, yeah? So, let's go inside. Aluminium, casted aluminium. This thing, this notch here is used as a cooling for the dramatic circuit. Well, not really. This is how it looks. We'll try to show you. We have input from the external antenna, the first MMIC, the integrated amplifier. It goes to a SAW filter, surface acoustic wave filter of 1575 megahertz. That's a bandpass filter, a very narrow bandpass filter. And then back to the second LNA and to the antenna itself. Yeah, and a little bit power supply, decoupling, and the biasing resistors. I will show you that better on the schematic. Well, that's the whole that's the whole magic. And now perhaps you know there's not enough power for that. 40 meters, come on, no way. 5 to 10 meters, 10 meters, and only for the E1 and G1 frequencies. That means GPS, Galileo, Baidu, 1575 megahertz. No GLONASS. GLONASS only with more power than that. So, let me show you. Again, this is how it looks. All the inductors are PCB made, inductivities. I do not want to take away the heat compound, heat sink compound. You will see how it looks beneath that on the schematics and on the data sheets. So, hi guys, let's start. By the way, I have a new toy. Kunkin 400 watt electronic load. I made already all the changes inside, and I will make for that an PCB, so you can use standard banana plugs, because I do not like to change the original ones. But okay, just for you for now, this information. Okay, we have our beautiful kit, and the schematics, completely reverse engineered. Guys, I have to give you some more information here so we understand how this repeater works. First of all, the satellite the GNSS, the signal from the GNSS satellites is very low. It is, in the worst case, down to minus 165 dBm. Depends on if it is in a city, if it is an open, completely open environment, etc. But calculate normally with 150, minus 150 dBm. This is what you get in a city environment. Between minus 125 dBm and minus 130 dBm is in a completely open sky. But this is best case, forget that. calculate with that. So, you know what that means, 155 dBm, that's noise. That's completely in the noise. To extract this from the noise, you need an extremely sensitive spectrum analyzer, an extremely low noise amplifier up to 60 dBs plus, at least, to see, I don't know, something that comes out of the noise. So now we have the chipsets for the receivers. The actual chipsets at the moment is a U-blox and the Chinese clones. They are very sensitive. They have a sensitivity down to minus 165 dBm. That's great. This is why you saw a lot of satellites on the software that I showed you appear. That's a U-blox center, by using this Neo M8N, a very sensitive, a quite sensitive chip or module. But there are a lot of professional equipment that are using older ones, like the Furuno, that's a chipset, a Japanese professional chipset, GT-8031, that has only a sensitivity maximum minus 138 dB. Here we have a problem with the repeater. It will not, with the U-blox I can use the repeater that I showed you, this one here, up to 5 meters or a little bit more. With the Furuno chipset, I don't know, 2 meters, 1.5 meter. Let's say 1.5 meter or 2 meter maximum. And I tested that and it's not satisfactory. Let's forget it. So this receiver is not the best one. This repeater is not usable for me, at least for the purpose I needed it, for quite older ones, quite older chipsets. There are a few calculations here that I wrote, and this is the schematic. You have the power supply, just a 7805 standard 5-volt regulator that gets quite warm. 9-volt input. We have the SMA connector here. This goes through a chock, an RF chock. Through this chock, the 5-volt for the active antenna are supplied. Then we go through a DC blocking capacitor, and then we have the first LNA, the first MMIC. This is the one, let me show it to you here. Low noise cascadable silicon bipolar MMIC amplifier. This is what they use. It's old, it's really old, yeah. It has a good amplification at 1.5 gigahertz, 25 dB, nominal. It is, when it is biased, at 10 milliamps. But this is the schematic. Here you see the biasing resistor, 4 volts at 10 milliamps. When the VCC is 5 volt, this one is 100 ohms. But we have, oops, that's the wrong one, sorry. As you can see here, the output power is only minus 2 dBm. This is very, very low. And you will see the second one goes directly to the antenna. So this is why this thing is not very powerful. So this is these are the LNA schema datasheet. And now the reason, after that, we have the biasing part of the, let me make it bigger, the biasing part of the LNA that is supplied with 4 volts 10 milliamps. It's a 100 ohm resistor. Again, blocking capacitor, DC blocking capacitor. And now we have the SAW filter, surface acoustic wave filter. This is a very, very narrow bandpass filter, more or less, mostly ceramic filter. After that, we have a DC blocking capacitor, a blocking capacitor DC, even that we would not need that because this is already blocking DC. And we have the second LNA that amplifies the weakened signal because of the losses of this SAW filter. And normally we have 25 dB at an amplification here, minus 2 dB insertion loss of that, plus 25, you would say it's 48 dB. Yeah, well, it's not. The datasheet gives a repeater total gain of 30 dB. That means this antenna is not very good. Yeah. Second LNA, biasing again, 4 volt 10 milliamps, and whoops, out to the antenna. Yep, to this antenna. It's not real big gain, but okay. This thing is, everything is very, very low noise, low power. So this is the schematic. This is the whole caboodle, this is the whole thing, this is the whole magic. Now, why can't we see any GLONASS? We are seeing a lot of Galileo, a lot of GPS, the software what I showed you before. The reason is this SAW filter. Again, quite an old filter. It's from the 90s, the whole stuff. As you can see here, the pass bandwidth is only 5 plus minus 5 megahertz. That's very, very narrow. That means that you could pass the 1600 with a center frequency of the 1575. You could pass the 1600 of the GLONASS, but look at this diagram. Here we have the center frequency, 1575. And here we have plus 5 megahertz, minus 5 megahertz. As you can see, the two cursors. Oops, how it is. Yeah, cursor 1, 1.570, and the other one is 1588800. So it's very narrow. From the spectrum analyzer here, we have a span, center frequency 1575, and a span of 300 megahertz. 300 megahertz is how many divisions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means 30 megahertz per division. Here, normally, if this is 5 megahertz, this is 30 megahertz. This here would be 1600 megahertz. And you are already a lot of attenuation here. Here, this would be the 1600 megahertz if you put a cursor more or less here. And you will see we're already down to the lower than 3 dB a lot. This is why the GLONASS with this not real strong attenuation, amplification, and the distance of 5 meters is not showing up. If I would put the repeater to 1.5 meters or something, I would get the GLONASS too. Guys, the video is getting long. Sorry, but I have to make it in 2 parts. This is the first part with some more informations on GPS and RF over fiber. The second part will be about a very low cost repeater, this one, in combination with this antenna. This is a kit. Again, completely reverse engineered and with a lot of details and explanations. So, I spoke about the RF over fiber. I don't know if anybody is interested. I'm reusing the already printed papers. If anybody is interested on more information about concerning RF over fiber and the design of such systems, let me know. Perhaps I will make a video. I worked with those things for quite a long time, and now in my professional job, I think it's called like that, it's a small part what I'm doing, and I'm using only RF over fiber because of noise issues and other issues. So that's the end of the first part. This is how it looks. It's a cheapie. It's built as a cheapie. You know, look at that. It is, what of that costs 1,000 euros? Nothing. Yeah. Anyway, if you like what you see, if you like my videos, if you like the way I show you my videos, please subscribe to my channel, press the like button, press the notification button. All this will help me to show you much more. As you see, I have a lot of, I hope interesting stuff to show you. That's for today. Thank you very much for watching, guys. See you. Cheers. So, and by the way, this is what I mean. If you get it near to 1.5 meters, we have the GLONASS too. This is a distance. You see it here. It's 1.5 to 2 meters. And we have a clear reception of GLONASS too. Just for info. Cheers.